Okay, so if you have two objects that are at different temperatures and you put them in contact with each other, heat will flow from the warmer object to the colder object, and the heat will continue to flow until both of the objects are at the same temperature. We call that thermal equilibrium. Conservation of energy says that you can't lose or create energy. You can only transfer it and change its form. So the amount of energy, heat energy lost by the hot object has to be equal to the amount of heat energy gained by the cold object. Just like when we make a monetary transaction, if I buy a Snickers bar for $2, I lose $2. The person selling the candy bar gains $2. It's the same amount of money, it's just transferring between two people. So we can define one object, one substance as the system and the other as the surroundings. And then we can say that the heat gained or lost for the system is equal to but opposite in sign to the heat gained or lost by the surroundings. The amount of energy is the same, it's just the direction, the sign of it that's different. So looking at an example here, we take a block of metal at 55 degrees Celsius and put it in some water at 25 degrees Celsius. So a hot block of metal in some cooler water. The metal's going to get cooler, it's going to cool down, and the water's going to warm up. Thermal energy transfers heat from the metal to the water. The exact temperature is going to depend on a couple of things. The masses of the metal, the mass of the water, and the specific heat capacities. So we can calculate the energy for the metal. Q equals mc delta T. All right, we learned that. Q equals mc delta T. So the heat lost by the metal is equal to the mass of the metal times the specific heat of the metal times the change in temperature for the metal. The metal's going from a higher temperature to a lower temperature, so its temperature change is negative. So in this example, this value is going to have a negative sign on it. We can calculate for the water. Let's just ignore the negative sign for a minute. Q for the water is equal to the mass of the water times the specific heat capacity of the water times the temperature of the water. The temperature of the water is going up, so its delta T is positive. So this was a negative number. Q water is a positive number. How can Q metal equal negative Q water? Well, it's absolutely fine. Let's just say that Q metal is minus 5 joules, right? And Q water is positive 5 joules. So if I put those numbers into this equation, negative 5 joules equals negative times 5 joules. Does that work out? Yeah, it does. So this negative sign is not saying that this one is negative or that the other one's negative. It's just saying that the two things are opposite in sign. If one's positive, the other's negative. If the first one's negative, the other one's positive. Okay? So let's do an example. Block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? Can you think of an easier way to answer that question? Just stick the piece of copper on a balance, right? Wouldn't that be easier? Yeah, but it wouldn't illustrate this process. So this is one where it can be helpful to draw pictures. It never hurts to draw a picture, and the picture does not have to be beautiful. It just has to represent what you're looking at. So here's a beaker with water in it. Water's blue, right? And then we've got a piece of copper in it, a block. So I'm going to put a block of copper in there, and I'll make that, copper colored because I can. So let's pull the information out of the problem and write it down. So the block of copper has an initial temperature of 65.4 degrees Celsius. Since I have colored markers available, I'm just going to use color to code this instead of subscripts. So the initial temperature for the copper is 65.4 degrees Celsius. It's immersed in a beaker containing 95.7 grams of water. So that's the mass of the water. Mass of the water equals 95.7 grams at 22.7 degrees Celsius. That's the initial temperature of the water. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. So that's the final temperature of what? Of both of them, right? So T final for the water is 24.2, and T final for the copper is also 24.2. And they're asking what's the mass of the copper. So mass equals question mark. So the equation that we need here is Q equals mc delta T. We can calculate the heat lost by the copper and the heat gained by the water, and we've got one piece that's missing. So Q equals mc delta T. We're going to try to calculate Q. We have mass for the water, so maybe we'll focus on calculating Q for the water first. We can calculate the delta T. Let's go ahead and do that. So delta T for the water is the final minus the initial. So it's 24.2 minus 22.7, which I think is 1.5. So we've got M, and we've got delta T, and then specific heat capacity. If it's not given, we have to go look it up. So I'm going to go back to that table. Table 7.4. So there we've got specific heat capacity for water is 4.18 joules per gram degree Celsius. And then as long as we're here, let's look at the copper as well. It's 0.385. So for the copper, specific heat capacity is 0.385 joules per gram degrees Celsius. And for the water, it's 4.18 joules per gram degrees Celsius. So I'm going to choose to look at the block of metal as the system. And so we can say that the Q for the copper is equal to negative Q for the water. So if you don't have orange and blue pencils, how can you indicate these are different? Well, the H2O would be a subscript here, and maybe Cu there. Which one of these do I have all the pieces for? For the water. So let's calculate Q for the water. You can put the whole thing together and solve it and have a big mess, which if you're good with algebra might be the way to go, or we can take some pieces and then put them together. So that's the approach I'm going to take. So we're going to find Q for the water. It's M for the water, C for the water, and delta T for the water. So the mass of the water is 95.7 grams. We looked up the specific heat capacity, 4.18 joules per gram degree Celsius. And we calculated the change in temperature as 1.5 degrees Celsius. .5, 95.7 times 4.18 times 1.5. So this equals 600.039. It would only have 2 sig figs, but I wrote the others down. I'll just leave them alone. And the units there, degrees Celsius cancel and grams cancel. And so this is 600 joules. Q for the water is positive because the energy went into the water, right? So this says that the Q for the copper is equal to -1 times the Q for the water. So Q for the copper equals -600.039 joules. What the water gained, the copper lost, right? That's the piece that students miss. They're like, well, I can calculate this, but then I'm missing things for this. What one loses, the other gains. And so if you can calculate for one of them, you just change the sign, and that's the number for the other one. Yeah?
Q is always represented in joules?
Well, Q is heat, which has energy units, so it could be joules or kilojoules or calories, but typically joules or calories in chemistry.
So Q in this situation would be 600.039? Or?
Yeah, 600.039 joules.
Okay.
Yeah. So for the copper, Q equals MC sub S delta T. We know what Q is, we know what C is, we know what delta T is. What we're trying to find is M, right? So we need to rearrange the equation. So we'll divide this side by C and divide that side by C. We'll divide this side by delta T and we'll divide that side by delta T. Just to save a little space, I'm going to clean it up here. Just erasing all the crossed off things. So the mass of the copper is equal to Q divided by C times delta T. Well, we just figured out what Q was. It's minus 600.039 joules divided by the specific heat capacity for copper and the change in temperature, which we haven't calculated yet. So delta T for the copper is the final minus the initial, 24.2 minus 65.4. Yeah?
When we look up the specific heat capacity, it's going to have the units always with it, right?
Yes. When you look up specific heat capacity, the table should show you the units. If you look it up in the textbook, it's showing you joules per gram degree Celsius, which is generally convenient for what you need. If you ask Siri or Google to find it, you may end up with SI base units, like pascals and kilograms and kelvins. And so you might have to, yeah. Look around, you can find it in the units that you need. 24.2 minus 65.4. So this temperature change is negative. Negative 41.2. Just barely fits in the corner there. Can we have a negative temperature change? Sure. It just means that the temperature went down, right? In a situation like this, you're always going to have one positive energy change and one negative. You're going to have one positive temperature change and one negative. Because the mass and the specific heat capacity have to be positive. You can't have negative mass. Not in real life. Okay, so down here I've got negative 41.2 degrees Celsius. And the degrees Celsius cancel and the joules cancel, and I've got 1 over grams, which is grams. So, you know, it's your calculator. You put in minus 600.039 divided by 0.385 divided by negative 41.2, and I'm going to get 37.82. I should have two significant figures because of this temperature change, and that's grams, and so that would round to 38 grams. Yes.
I did this the long algebra way, where it was the same thing, and I ended up with a negative value for grams because of the negative temperature change. Is it okay to just do all the math normally and remember that copper lost heat here, so change the sign at the end?
Usually that is okay. So what happened is, if we examine your algebra, we'd find that you lost a minus sign somewhere.
Okay.
Yeah. Because you can do it all out, and as long as you don't miss any little details,
Yeah.
it does come out exactly correct.
It canceled in your example because you did the negative numerator for the loss of heat there, and I only have the 1 minus sign on the bottom.
Yeah, so up here you have to have Q equals negative Q. So if you miss that minus, then it doesn't get canceled. Yeah. So some of this with the negative signs, you come up with negative mass, and sometimes it is okay just to say, shoot, I lost the minus sign, and just make it positive. You do need to be careful, though, because occasionally it's negative there because you did something else wrong. So just be careful. Anybody else have any questions? Yes?
So I got lost when we used the 41.2 for delta T.
Mm-hmm.
Because we had delta T as 1.5 degrees.
So this is the change in temperature for the water,
Oh, okay.
and this is the change in temperature for the metal.
Thank you.
The changes in temperature are not the same because the masses aren't the same and the specific heat capacities are not the same. And so I like using colors on this example because when you're just sitting there looking at it, I think it helps to just immediately identify, oh, this is about something else. When you're writing this out with a pencil, though, you have to specify, like I did here, and you have to have a whole bunch of subscripts to indicate Q for what, M for what, delta T for what, because they're all different. Nope, I already did that one. Got lost, sorry. 37.8. I don't know why they did that. They didn't pay attention to their sig figs is why. Okay, so we talked about change in internal energy is equal to Q, the heat transferred, plus work. So there are different types of work. One type is called pressure volume work, and this occurs when a force caused by a change in volume acts against an external pressure. And this is the sort of thing that happens in an internal combustion engine. You have the gas exploding here, and the volume change creates a force that pushes against the piston, against pressure, and it does work. And so then your engine is able to translate that through several different things into forward movement of your vehicle.
So I have a question. On the last one, I know you moved on already, but you said you used two significant
Right.
And that is because of the 1.5 degrees Celsius, right?
Yeah.
Okay. Since you calculated the 1.5, but it was derived from two numbers that had three significant figures.
But it's
that's
subtracting
So if you subtract, then it goes with whatever the result
the
is.
decimal place.
Okay.
Yeah. Yeah, so that's one of the, we don't run into the mix of adding and subtracting versus multiplying and dividing with sig figs very often, but this is one example where it shows up. So because we subtracted the temperatures that had one decimal place, when you subtract, it very commonly happens that you end up with fewer sig figs, or sometimes more sig figs than what you started with. And so that's why you have to look at this subtraction separately. The good news is that on a question like that, on an exam, I won't be tricking you about sig figs, right? You won't get it wrong just because you put the wrong number of sig figs. But mastering chemistry, as some of you have seen, can be a little bit picky about that. It's better than it used to be because it'll say, yeah, but I asked you for 2 sig figs and you're giving me some other number, try again. And it'll let you try again without deducting points as long as you have the correct overall value. But that can still be a little frustrating if you're iffy on your sig figs. So here we have pressure volume work, and here we can examine a piston separate from the engine. So here we have the initial state, and there's a volume here. And when this expands, it's going to push the piston up. And so it's going to exert a force through a distance. The change in volume is the area of the piston times the change in height. So a force is, work is a force times a distance. And so that's what we've got going on here. So the change in volume is going to be positive in this case when the gas expands. But as our sign conventions tell us, the work here for the system, the gas, should be negative because the gas is doing the work. It's putting out, so it's a negative. So work here is the external pressure times the change in volume, but in order to get the sign to work out, we have to put a negative here. So W is minus P times delta V. So if we use atmospheres for pressure and liters for change in volume, we end up with a unit of atmosphere liters, which doesn't look like an energy unit. And so this is the conversion here. 101.3 joules is equal to 1 atmosphere liter. And the simplest thing there is just to say, okay, I believe you. All the units work out really cool, but most Chem 1A students are not interested in that. So there it is. And I'll give you that number, that relationship on an exam. Yes?
So for this, we're not worried about why the gas is expanding?
We're not worried about why the gas is expanding. It just is.
Okay.
Yeah. Now, could we calculate stuff using the gas laws? We could. And in an internal combustion engine, the reason that it's expanding is because in that chemical reaction, you're generating many moles of gases that weren't there before. So that's why it expands. So a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters, the final volume is 1.245 liters, how much work in joules is done? So we have 1.58 atmospheres. It says that's the external pressure. And then we have an initial volume of 0.485 liters. It's the initial volume. And we have a final volume of 1.245 liters. It's asking for work The equation we just learned is that work is equal to negative P delta V. So I have the external pressure, but I need the change in volume. That triangle, delta, means final minus initial. So the final minus the initial. I don't want to encroach in my space over there too much. 1.245 minus 0.485. My calculator tells me 0.76. But if I'm paying attention to my significant figures, which I should always try to do, when I'm subtracting here, this number has 3 decimal places and this number has 3 decimal places. And so the answer should have 3 decimal places, and it only has 2. So I need to add a 0. Because that was 5 minus 5 in that 3rd decimal place. It's not unknown. It's uncertain, but it's not unknown. So 0.760 joules. So then I can plug my values in here. Negative times the pressure and the change in volume.
So it's not liters,
You caught me. It's liters. Yeah. I don't know where that came from. It's liters. I'm just skipping ahead. Ooh, almost. Yeah, thank you. It's liters. 0.76 liters. Would have figured it out eventually, but you saved me some time, so thanks. So for this, I'm getting minus 1.2008 atmosphere times liter. And this should have 3 significant figures. But I need joules, right? And so we had that relationship, 101.3 joules is equal to 1 atmosphere liter. I don't expect you to remember that, but you should know that it exists so you can go look it up. That 101.3 looks a lot like the 101,325 pascals, right? And that's actually where it comes from. So I'm going to multiply so that I get joules on top and atmosphere liters on the bottom. 101.3 joules for 1 atmosphere liter. Atmospheres cancel, liters cancel. So the work here is minus 121.6 joules. And then when I round that, I get minus 120 joules. No, 3 sig figs, not 2. It's like, wait a minute, that doesn't sound familiar. There we go. 3 sig figs, so 122 joules. Questions?
This is negative.
It's work being done by the gas. Yes, it's work being done by the gas.
So if it was pressure being exerted on the system, it would be positive.
Yes, if we were looking at work done on the gas because an external pressure was compressing the gas, then the change in volume would be negative. And with the negative sign in the equation, we get a positive value for work. Yeah. And, minus signs have probably plagued you throughout your math classes all your life, right? As soon as they introduced what it was. Because they're really easy to overlook. and they're easy to just lose, and stuff happens. And so with a calculation like this, take advantage of your calculator. And if you have a negative number, type it in as a negative number, and then if you're adding negative numbers, your calculator can take care of that for you, and you don't have to mess it up. Yeah.
Pro tips for, like, I typed in a negative number in my denominator,
Mm-hmm.
and then it gave me a syntax error.
So your calculator has a minus button and a change sign button,
Oh, okay.
and they are very different.
Okay.
Yeah, so that's the problem. If your calculator doesn't have a change sign button, and on the TI-36X Pro, it's a negative in parentheses. And that's what you use to make a number negative. You punch that in first, just like the negative sign comes first before the number, and then you type the number in, and you're fine. If you use the minus sign, sometimes it'll work, and sometimes it will not, but dividing, yeah, won't work. Any other questions? Minus 122 joules. Okay, here's another one. When fuel is burned in a cylinder equipped with a piston, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is delta E for the burning of the fuel? So here we're looking at the heat exchanged and the work done. Because when the gasoline explodes inside a piston in your car and moves the piston, does all the energy from the chemical reaction go into the movement? No. We lose a lot to heat, and that's why the engine gets hot, right? We say it's lost. It isn't lost, but it's lost to usefulness. Okay, so the volume expands from 2. So volume initial is 0.255 liters, and the final volume is 1.45 liters. And we're going to need delta V, so let's just calculate it right away. 1.45 liters times minus 0.255 liters. I'm going to put the units in there so I don't screw that up again. 1.45 minus 0.255. So the change in volume is 1.195 liters. And what about sig figs there? Should have 3 sig figs because, not because these both have 3, but because this number has 2 decimal places. This number has 3 decimal places, and so the answer should end in the second decimal place, which happens to mean that it has 3 significant figures, but maybe not for the reason we thought. Okay, so that's the change in volume against an external pressure of, so P external equals 1.02 atmospheres. In addition, 825 joules is emitted as heat. Whoops. So Q equals, so it's 875 joules. Is that a positive or a negative number? If it's coming in, it's positive. Emitted is going out. Right? So it's emitting, it's giving off, and so this Q is negative. This is where the sign, the direction, is given by the words. Well, can we calculate the work? Sure we can. The work equals negative P delta V. So negative times the pressure, 1.02 atmospheres, times the change in volume. Seems to be someone stomping around on the roof. So negative 1.02 times 1.195 equals 1.2189 atmospheres times liters. Both of those numbers have 3 significant figures, so this value has 3 significant figures. Now it's asking for delta E for this process. The change in energy is heat plus work. Each of those could be positive or negative. They could both be positive, they could both be negative. There's any combinations possible. So here I have negative 875 for Q. Negative 875 joules. Plus W, but I can't add joules and atmosphere liters. The units have to be the same, so I have to convert my work into joules. So the atmospheres cancel and the liters cancel. So this is negative 123.47 joules, still having 3 sig figs. So then I have negative 123.47 joules. So here I have a negative number and I'm adding a negative number. That can cause problems on your calculator, so just use the change sign, the minus sign. So negative 875 plus negative 123.47. And so that gives me a negative number, negative 998.47 joules. Here I'm adding. This number ends in the ones place. This number ends in the ones place. So my answer should end in the ones place, and I'll round that to minus 998 joules. The point of these sorts of problems is not to get the correct number of significant figures, but I'm just going to explain it as I go along just to reinforce. Any questions? Minus 998.